So what did you get when you factorised this? The easiest way to factorise this is to look for the common term. Common term. Normal 3. X. So if I factorise the x out, that's x squared minus x minus 2. And we can factorise this bit. What's this bit? No one's talking because you can hear your voice, right? Is that what it is? X plus 1, x minus 2. So now we've factorised it, and now we're going to solve for the x-intercept. So the x-intercepts are
0, negative
0, negative 1, and 2. Okay. So the reason why I wanted the x-intercepts is because I'm going to do a rough sketch of this graph. So this is a cubic graph. It's a positive cubic graph, so it has that shape. So, and it cuts the x-axis at negative 1, 0, and 2. So I'm just doing a rough sketch. Looking at this, assuming that the turning points are between the two intercepts, where do you think our minimum turning point is? Yeah, around the 1. Yeah, so it's between 0 and 2, so around the 1 part. What about our max turning point?
I'm getting pointy.
Negative Alright, so what this represents here is if I was to graph the derivative graph of this, I'm going to do the y-axis right underneath. So I'm going to line up the y-axis and the x-axis are parallel. What happens when we have a turning point? Say this is our derivative graph. Say that we're graphing the derivative of this. What can we say about the gradient at
0
equals 0? So what we're going to do is at x equals negative 1/2, so just line it up at x equals negative 1/2, where would the derivative graph cut the x-axis? Yeah, yeah. What about this turning point here? Do you think it would also cut the x-axis at 1?
Yep.
Okay, so now looking at this is a cubic graph, so what would the derivative of this graph be? Parabola, yeah. A quadratic, yeah. And it would be concave up, concave down, what do you reckon?
Concave up.
Concave up. Okay, so the derivative, you look at it, so I'm just deriving that function. It is a parabola, it's concave up. So even if you don't know what the equation is, see this part here? All the gradients here is positive. Do you agree that from here to here the gradient's positive? So that positive corresponds to being above the x-axis. I think we did a little bit of this 2 lessons ago. So yeah, a little bit. So the positive gradient here corresponds to being above the x-axis. So if these gradients are negative, that's telling us it must be below. So that means between negative 1/2 and 1, it's all below the x-axis. And between 1 and beyond, it's all above the x-axis. So that part here tells us that the derivative, so I'm using y dash. Y dash is increasing, so it's positive. And this part here tells us that the derivative is decreasing, so it's negative. Alright, so now we're going to use this graph. So I'm going to draw it again so I can line it up again. So 1/2 and 1. Assuming that the turning point of this graph is also halfway in between, what number do you reckon? We'll just give an estimate.
0.25.
Yeah, 0.25. So an estimate is around 0.25. So I'm line once again. Once again, lining up the y-axis. So this is the y dash, this is y double dash. This is x, x is parallel. So this is about a quarter, was it? Yeah, so around a quarter. This graph here cuts the x-axis. But what kind of graph do we have? We've got a parabola now. In the second derivative, the graph would be a line. Okay. And this part here is, what's its gradient?
Negative.
Yeah, negative, so
Below the x-axis.
below the x-axis. And this part here is positive, so it's above the x-axis. But if you actually assess this as just the second derivative, can you say that the gradient of the second derivative is greater than 0?
Yes.
Yeah, it's a positive gradient. So being a positive gradient tells us that if the second derivative is greater than 0, it's concave
Up.
up. Which if you look at this graph is a concave up. So that's the relationship between all three graphs. So now the fun part is, in your HSC, you don't get questions like these in your textbooks, but in your HSC, they'll give you a graph. So we're going to go backwards now.
Love going backwards.
Backwards. So instead of a positive line, I'm actually going to do a negative line.
I know what you're
Oops, no, that's positive. Negative. See, I told you.
But you can tell the camera is.
No, I'm not going to tell the camera.
No, so you're going to stop it, do it again, and then start it.
So we're going to have a negative gradient. Say it cuts it at 3,
So, sorry, why are we having a negative gradient?
because we're going backwards, and I didn't want to use the same one. Because if we have a positive gradient, essentially when we go backwards, our graph is going to look exactly like that example.
Well, now we know it's
Isn't that the idea?
just upside down.
Yes. Now we know that it's going to be upside down. So now you're connecting the ideas. So this is our second derivative. So when our second derivative is less than 0, we have a
Okay, then.
concave down. So because we have a concave down, what happens at the 3 turning point? That's excellent. Because it's a concave down, what kind of turning point do we have?
already turning point.
Maximum.
Yeah, max turning point. So this tells us that at 3 we have a maximum turning point. So I'm just, there isn't really good. So I'm just going to pick some arbitrary points. Say this is -1. Say this is 3. So the distance between -1 and 3 is 4. So this is 7. Now this is our first derivative. So how are we going to go backwards from our first derivative to our original? Well, apart from integrating, using this graph, how would we go backwards? So now we have linear, quadratic, so our next one must be,
Just use the positive and negative.
yeah. So the next one is cubic. Where are our turning points for our cubic graphs? Where will they be?
1.
Yes. So we'll line it up, so -1. And at 7.
So idealistically, we can choose any
Yeah.
numbers.
It doesn't really matter because, you know, when you integrate, you have to plus C. When you plus C, your graph could be shifted upwards. It
Okay.
should be shifted downwards. It doesn't matter as long as your turning points all line up at 3.
Okay.
So I'm choosing the points myself just to help you understand this. So we have turning points at -1 and 7.
How
Okay.
did you know that? It says you know it's -1.
So I made the points up.
Oh.
Well, I was saying before that because of the plus C when we integrate, it doesn't matter if the graph shifted downwards or shifted upwards. I've just chosen these points so that I can actually move on. So most of the time in your HSC, they'll ask you a question involving, say, a linear graph to a quadratic. And they'll just ask for the general shape. They won't give you specific points. They'll just be like, what shape is the primitive function of that shape. So now we're integrating. We have a turning point at -1 and 7. So positive cubic graph was what shape? Positive cubics were this shape. So what happens if it's a negative cubic?
The other way around.
Other way around. Other way around. So that means, where do you think your minimum turning point would be? Is it at the 7 or at the 1? Negative 1, yeah. And your
Maximum is at 7.
7. So once again, this is just a rough sketch. It's not exact. If you had something shifted upwards, that'd still be correct. Or if you had something shifted downwards, it'd still be correct. Just as long as your turning points are at 7 and negative 1. So let's look at point of inflections here. Let's go back to this diagram because this diagram is actually neater. So our point of inflection occurs where? It occurs when and where?
I forget what the point of inflection is because we go too fast.
In between the maximum and the
Close.
Okay, so it's in between the maximum and the minimum turning point. So
What's the difference between point of inflection and turning point, or a stationary point and all that stuff again?
stationary point is when the graph momentarily stops and changes directions. Stationary points and turning points are similar.
It's not the same.
No.
Well,
Turning points, you can only use turning points to describe min and max. Turning point, I'll write it down. Turning points only for min and max. Stationary points includes point of inflection, no, min max, min plus max, and horizontal point of inflection, not any point of inflection, horizontal point of inflection. Point of inflection occurs when the concavity changes. So see how the concavity here was concave down and that's concave up?
Yeah.
So it changes, so we have a point of inflection. So this point of inflection actually corresponds with, although I didn't do it really well, it actually corresponds with that turning point. Can you see how it corresponds with that turning point?
Yeah.
Yeah? And if you go one down at that turning point, that negative a quarter is where, that negative a quarter is actually when the second derivative equals to 0. That's your point of inflection, isn't it? Okay. Discussion.
Yeah. Do we have to do it with the triple graph stupid structure thing or not? Or can I have 3 separate
Does
graphs?
that make sense?
Oh, as in like combine all three together?
Yeah, do we have to do that or not?
No, I wouldn't do that myself, no.
Thank you.
I haven't seen it being asked yet. Usually, this is actually just one of those 1-mark questions. It's usually in multiple choice. I think they asked it in the 2013 exam. They gave you a line.
So chances are we probably won't get it.
They'll give you a line. It's good to know. They'll give you a line, and then they say which one is the primitive function, or which one is the integral of this graph. So they'll say this is the second derivative. What's the first derivative? Or typical question is usually what's the primitive function. So that's pretty much going from here to here. And if they asked that last year, you may get this one going to this one. So the opposite. But there's a lot of things the HSC board can assess you on. This is just very good to know. So basically, let's go back to this one when we go backwards. Can you see now that 3 is your point of inflection? So say 3 corresponds to the point of inflection here, and 3 is also the turning point here. Yes? No?
Mm-hmm.
Usually, so if you were given the graph for your second derivative, wherever the x-intercept is usually the horizontal point of inflection. So x-intercept in a second derivative graph corresponds to point of inflection.